Hello, hi everyone. Good morning. This is Kalyana from Radiant Semiconductors. Welcome back to the technical session on the SDC file, synopsis design constraints file for timing. So SDC is a short form of synopsis design constraints. Okay, so SDC is a common format for constraining the design, which is supported by almost all synthesis tools, physical design tools, that is place and route tools, and any other tools like STA tools, right? So generally, timing, power, and area constraints of design are provided through the SDC file, and this file has extension .sdc. Okay, so SDC file syntax is based on tickle format, and all commands of SDC file follow the tickle syntax. So in SDC file, hash is used to comment a line, and colon is used to break the line. Okay, SDC file can be generated by the synthesis tool, and the same can be used in for PNR. Okay, so SDC basically refers to synopsis design constraints file. Okay, so SDC file is generated from the synthesis tool, as we can see in this image, right? So when the SDC file is getting generated from the synthesis tool using the write_SDC command, right? So initially synthesis tool has to receive the inputs from the RTL team. Okay, so this is where we have set of design constraints. Okay, now what does set of design constraints mean? So when we are starting the synthesis, we need to receive the timing constraints in tickle format from the RTL team. So what does these timing constraints in tickle format contain? So the timing constraints in tickle format contain mainly the clock definitions. How many clocks are there? Clock definitions. What is the clock frequency associated with the clocks that are defined in the design constraints in tickle format, right? And what are all the timing exceptions that are present in the design constraints of the tickle format? So these are the main things that will be present in the design constraints file, which is nothing but tickle constraints file from RTL team. Okay, now with the help of clock period, right, as we know 1 by f is nothing but clock period. So with the help of clock period that is defined in the timing constraints or the design constraints given by the RTL team, we need to try for enabling the logic, right? I mean fitting in the logic. Okay, so that is where in the logic synthesis we are trying to optimize the design so that we can meet the desired clock period. Okay, so we can meet the clock frequency. That is where your logic synthesis tool has to help us out in meeting the performance of the design, right, which is defined by the RTLT in the format of design constraints, right? And of course in the logic synthesis tool we do add other kind of constraints. For example, how much should be the uncertainty, any other kind of design margins which we want to add, right? For example, path margin, right, or like guard bands, the derating which we want to use. Okay, all the different kind of design margins which we want to use will be added up in the logic synthesis tool. Similarly, if we want to add, let's say, interface timing related constraints, for example, set input delay, set output delay, right, even those constraints as well can be added in the logic synthesis tool. So that will be written out in the write SDC file, okay, which is the output of synthesis, right? I mean the file extension is .sdc file. So this .sdc file contains additional constraints that are coming from the synthesis tools. Okay, and now this SDC file is read into the place and route tool. This is called as functional SDC file. If we are doing DFT, that is design for testability, in order to have the controllability and observability of the design, then in that case we try to add DFT related constraints as well. They are called as test mode constraints, right? I mean which are related to the scan, right? And even we can have MBIST related constraints as well, JTAG related constraints as well. Okay, so these are the additional test mode constraints which we are giving it as input to the place and route tool, along with the read STC that is defined in the place and route tool. Okay, so the read SDC not just contains the functional SDC from the logic synthesis tool, it also contains the test mode SDC, right, from the DFT team as well, if at all we are doing the DFT. Okay, not just that, it also contains set driving cell, set drive, which are interface related constraints, set load, which is again interface related constraint. Similarly, it also contains set input delay, set output delay. So these are the additional constraints which are defined in the SDC file that is coming out from synthesis tool. Okay, now using this SDC file, we need to make sure that in synthesis we are able to comfortably meet the frequency coming from the design constraints. Okay, and similarly, along with the frequency, we should also make sure that if we can get the positive slack in the setup timing for logic synthesis, that positive slack will be used by the place and route tool in order to optimize the designs. Okay, so that will be the margin for place and route tools. So this is for logic aware synthesis. If it is physical aware, we can reduce this pessimism, we can reduce this margin, because already the physical aware is taking care of the floor plan, PDM network, and directly in the placement stage we are doing the legalization of the cells. Okay, now let's look at different parts of the SDC file, right? Now in the SDC file we have header, operating condition, wire load model, system interface, design rule constraints, timing exceptions, area constraints, multi-voltage constraints, and lastly logic constraints. Okay, so these are the different varieties of constraints that are present in the SDC file. Okay, so header will be containing the version and the units. Similarly, system interface will contain set driving cell, set load, right? And then design rule constraints will contain set maximum load fan out, set maximum transition. Similarly, timing constraints will contain create clock, create generated clock, group path, clock uncertainty, clock latency, input delay, output delay. Lastly, timing exceptions will contain multi-cycle path, false path. Okay, so these are all some of the constraints that are present in the main sections of the SDC file. Okay, now let's look at some of the details, right? I mean, as we discussed about the different type of constraints in the SDC file. First is SDC version. Okay, the SDC version is defined by a command called set SDC version. Okay, so this statement specifies the version of the SDC file. It could be 2.1, 2.0, 1.9, 1.8, 1.7 or more older also. Okay, just for an example, version 2.1 has been introduced in December 2017. Okay, we have latest versions as well, right? I mean, in 2025 we have latest versions as well, which will be defined in the set SDC version. Okay, so this defines the version so that it makes sure that the constraints that are present in that particular version of SDC file, they are latest. Okay, alright. Now units. What does units replicate? So units of various quantities like time, resistance, capacitance, voltage, current, and power can be specified using set unit command. Multiple units can be set using a single set unit command. Example, set units -time nanosecond, -resistance kilo ohm, -capacitance picofarad. Okay, -voltage V, -current milliamp. So SDC commands can be further categorized as follows. Some important commands will be discussed in the later sections. Okay, operating conditions, wire load model, system interface, right? Set driving cells specifies the drive characteristics of input or in-out ports that are driven by the cells in the technology library. These commands associate a library pin with input ports so that delay calculation can be accurately modeled. Right, I mean, what is the syntax for set driving cell? Set driving load lib cell name library name, right? Rise fall min max pin name, right? From pin name don't scale no design rule, input transition rise, input transition fall, multiply by factor clock. Okay, so these are all the different subcommands that are present in the driving cell. Okay, and example of driving cell is set driving cell hyphen lip cell, set driving cell hyphen lip cell, and to hyphen pin hyphen from pin. Okay, these are all the different parts of the set driving cell. Okay, now let's look at set load. Right, so this command sets the load attributes on the specified ports and the nets in the current design. The unit of load value will be the unit of capacitance specified in the unit defined in this file. Example, set 0.001 get ports. Okay, so mainly set load is used for output ports, and then set driving cell is used for input or in-out ports. Okay, now let's look into design rule constraints. Okay, in this part basically we are defining the maximum fan out, maximum and minimum capacitance, and maximum transition time are set. Okay, now design rule constraints are already defined in the library file. Okay, but then if you want to have a pessimistic constraints defined for the design rule constraints, then we can define them in the SDC file as well. Right, and the tool will take the values that are defined in the SDC file as compared to the values that are present in the library file. Now, what is the advantage of adding pessimism to the design rule constraints is it will help you to mitigate the electromigration problems, especially the electromigration problems, because the load on the cell will be reduced. Thereby, the current requirement of the net also will reduce. Okay, thereby reducing the current density in the net, and which will help to save the electromigration. Similarly, apart from electromigration, by reducing the load on the cells, automatically the yield of the cells will increase, the aging factor of the cells will increase, the cell delays will come down. If the cell delays come down, automatically the number of logic levels in the edge to edge path will increase. Okay, thereby we are able to meet the time period or the clock frequency effectively as defined by the RTLT. Okay, so these are several advantages. Right, disadvantages: because of pessimistic design rule constraints, we may end up with adding more number of cells than required. Okay, which will lead to area consumption, which will lead to power consumption. This is the disadvantage of the design rule constraints. Okay, all right, now design rule constraints, we can control the load on the cell through any of these factors. For example, capacitance, for example, transition, for example, fan out. Okay, through any of these modes we can control the design rule constraints. Okay, all right. Now let's look at the set max transition. Right, maximum transition time is set by this command, which is design rule, and set to clock port or design is set to a specific input port or design. So set max transition value hyphen data path. Transition again can be data path related or clock path related. Okay, so we can either have both, or we can have for even complete current design as well. Okay. Now coming to timing constraints, right? In this part, basically we set clock definitions, clock groups, clock latency, clock uncertainty, clock transition, input delay, output delay, timing delays, right? Now, when the design is in the ideal mode. So during the ideal mode, we don't have clock tree built up, so we can model the clock as per the propagated clock. Okay, so that those impacts can be taken up while optimizing the design in the ideal mode. Okay, so that's where we have clock latency, which can again be divided into two parts: source latency and network latency. Similarly, we have clock transition, which can be rise or fall transition. Right, now these things will be removed once actual tree is coming into picture post the CTS. Right, now this is the main advantage of the clock latency and clock transition. Now clock grouping can also be done. We can group the clocks, certain clocks, let's say asynchronous clocks or synchronous clocks, right, which can be used for later purposes. For example, skew optimization, it can be local skew or global skew optimization. Similarly, we can even inform the tool about balancing the skew as well. Based on the clock groups, we can define the false paths between certain clock groups as well, right? And of course, the clock definitions, it can be create clock, create generated clock, right? And similarly, right, input delay, output delay. So input delay and output delay, as we discussed, I mean, these are related to interface timing, where we are defining certain portion of the period for the outside of blocks. Okay, so when we are defining certain portion outside of the blocks, then what happens is in the period that portion of the period will be removed and the remaining portion of the period will be utilized for our current block. The same applies for into range and similarly for range to out. Okay, and then lastly timing derates. So timing derates, it can be flat derates, it can be OCV derates, it can be AOCV derates, it can be POCV derates, it can be LVF derates, right? It can be guard band derates. So there are varieties of derates that can be applied based upon the application. Okay. Now let's look at the create clock command. So create clock, we define the clock name, we define the source of the clock, we define period, waveform, right? We can either add multiple clocks for the same source, that is where we use the command -add. Okay, the create clock command creates a clock object in the current design. This command defines the specified source objects as a source clock. Okay, so create clock, okay, u13 z hyphen name clock hyphen period 30 hyphen waveform, create clock hyphen name ph12 hyphen period 10 hyphen waveform. Okay, so this is on the create clock. Now let's look at the create generated clock. So create generated clock hyphen name hyphen add source objects hyphen source master pin hyphen master clock, right? Hyphen divide by factor, right? Hyphen multiply hyphen duty cycle, right? Hyphen invert hyphen pre-invert hyphen edges hyphen edge shift, right? Hyphen combinational. The create clock generated clock command, right, creates a generated clock object. A pin or port could be specified for the generated clock object. Generated clock follows the master clock. So whenever the master clock changes, generated clock will change automatically. A generated clock can be created as a frequency divided clock, a frequency multiplied clock, an edge divided clock, or an inverted clock. The above example will generate a clock which is derived from the original clock named clock. The generated clock will have a frequency of 3 times of the original clock and time period will be 1/3 of the original. Okay, so 15 nanosecond will become 5 nanosecond. Okay, now let's look at the group path. Okay, so group path hyphen weight, right, hyphen critical range. This is very important group path which we regularly use for optimizing the timing paths. Groups are set of paths or endpoints for the cost function calculations. The group enables us to specify a set of paths to optimize even though there may be a larger violation in other groups. When endpoints have been specified, all paths leading to those endpoints are grouped. The create clock command automatically creates a group for the new clock with a weight of 1.0 and named the same as the clock name, right? So group path hyphen name group 1 hyphen weight 2.0 to, right? Similarly group path hyphen name group 1 hyphen from, right, hyphen 2. So we are defining the group. Similarly we are defining the weight as well. Okay, based on the weight the optimization will be performed. Okay, clock uncertainty. So set clock uncertainty, right, object list hyphen from rise from, right, and then fall from. Okay, rise to rise hyphen fall to rise, right, and uncertainty. After defining the clock, to take care of variance in the clock network, clock uncertainty added. Clock uncertainty adds some margin of error into the system to account for variance in the clock network caused by non-ideality of clock network and clock source itself. Above specified command can specify either interclock uncertainty or simple uncertainty. It sets uncertainty to the worst skew expected to the endpoints or between the clock domains. Right? So set clock uncertainty hyphen setup 0.5. Right? Similarly, clock uncertainty can also be added for rise and fall times of the clock as shown below. Okay, so set clock uncertainty hyphen max rise hyphen min fall. We can even define uncertainty for the hold as well. Alright, so these are some of the important SDC constraints which we discussed today. Right, we will go through some more constraints in the coming week to understand how these constraints will impact the performance of the design, how these constraints will impact the multi-voltage part of the design, how these constraints will help us to optimize the power of the design. Okay, so all these things we are going to go through in the next week's presentation. Okay, and stay tuned, and for more information please reach out to our website radiantsemi.com, or you can also feel free to write us out at info@radiantsemi.com. Thank you and happy learning.